Barrett, and University of Mexico, works Arithmetic.
So let me start by thanking the organizers for properly inviting me here. I didn't have to fill out a form or look online, find a conference. I just received an email that felt important. And they paid for it. So it was enjoyable to, be a part of good talks in the city and have fun. It's at least the second. So I'm going to build towards some notions of what might correspond arithmetically to holonomy in the geometric setting, and perhaps to make Alex feel better. I will start with things I presume everyone is familiar with, and end with things I pretty much know no one's familiar with, including myself. So let me proceed in this fashion. Say, actually, so we'll start with a fiber bundle. Say it's complex manifolds or non-singular C varieties, if you will. Complex manifolds is a principal G bundle. For, say, a Lie group. G, if it's a G torsion, or let's just say G torsion. So it's principal homogeneous space with respect to right action. E, that's also P. P's good. So it's a G torsion with respect to a right action of G on P, and this action is a morphism in the appropriate category if I choose to change category from C manifolds to something else. Okay, and given a principal G bundle, or more generally a fiber bundle, we can put a connection on this, and perhaps I'll take this approach so we can connection on P, and lift paths. We have M here. So let's call it H. With this notation H, I'm allowing myself to define a connection in Arithmetic fashion. This is some horizontal part of the tangent bundle of P, and we can lift paths on M to horizontal paths in P in an appropriate fashion. One can also use the specification of such a horizontal to define a projection onto the fibers of P, and then from that push forward and come up with a one form that represents the connections. How it's done, but I'll stick with this H for now. Maybe I'll say something about the other way in a bit. So we can put a connection on P, lift paths on M to P, and I should say that, I'll leave it like that for now, but I should say that this H is defined over points Q and P such that we can write the tangent space at a point Q, TQP, as some direct sum of the fiber, which is the kernel of the differential pi, and some HQ horizontal. It varies smoothly and is equivariant with respect to this right action of G. I'm going to squeeze that under the carpet. Given that, we can define this notion, the holonomy of this connection. Let's say Q and P this way. We'll write it as Hol Q of H And rather loosely, we'll say that this is all of the elements G in the gauge group G, such that G corresponds to, we say piecewise smooth. Okay, just said paths there, piecewise smooth paths. Should be precise there and here. I'll say loops, but I really mean piecewise smooth loops that we've lifted up to P at the point Q. Okay? And we can also restrict ourselves not to loops, but specifically contractible loops. And we'll call that the restricted holonomy. We put a little circle here, and these are simply the elements of the gauge group that correspond to contractible loops at Q. So we can, given a loop at Q, I should have said here that this action of G preserves fibers. So when we lift paths here, any of these loops corresponds to an action that preserves the fiber, and there's a correspondence between such loops and these actions, these automorphisms here, and the ones that correspond just to loops are elements of the holonomy, and the ones that correspond specifically to movement around contractible loops are elements of this restricted holonomy. And one can make a number of remarks here. There's some things to be said. In particular, one can show that some bullet points here. If m is connected, I should move rather quickly for PQ. P, and I'll use the arrows here to represent that Q and P are connected by some path. Manifolds connected, path connected. In the same path component, you can show that these groups are conjugate of one another. So you get this isomorphism, Hall. And this allows me to drop reference to the base point. So from now on, I'll assume connected, work on connected components, and then one can show that then, maybe I should put H's here, to be specific. With respect to this connection, Hall is a B group. Hall 0H, this is a normal B subgroup. Of Hall H. And with those facts in mind, we can define the monodromy group as this quotient. Say H minus as Hall H. So all of the automorphisms that come from non-contractible loops at points on M, or above points on M. They're monodromy group because there's a surjective homomorphism from pi 1 of M to this thing. In general, it's not an isomorphism. As a counterexample, you can take, we can consider a flat connection on a non-simply connected base space M. Then homotopically equivalent loops might correspond to different elements of G. So this idea of being curved allows homotopically equivalent loops to still correspond or still give you different automorphisms in the fiber of points in the base space. Straightforward in a sense, and maybe I'll, in this fashion, say for my definition, the actually this was a theorem, Zamro-Singer. Say it like this. Lowercase h, of course, A group. This is generated by one of these things. Is generated by a series of brackets of horizontal vectors, essentially. So this is analogous to what Alex showed earlier in terms of the delta i's in his way of describing this thing, and corresponds in a sense to one way in which Ambrose Singer is given in terms of covariant derivatives and Hall zero being generated by these commutators. These things. Okay, so we have an exact sequence. Relating the restricted holonomy and our monodromy here. And this is something that I developed because it's a relationship between these two things that we might want to try and replicate in arithmetic. It's one of several ideas. Okay, maybe I'll say in particular, so I'm starting geometrically, I'll proceed towards arithmetic, but there are a number of examples of monodromy appearing in algebra, which might guide what we might want to use over here in arithmetic. Maybe as an example, say of, let's just say mono. And AG say is to take a smooth, proper map of non-singular or smooth C varieties. This is topologically the fiber bundle. We can construct from such a thing a local system. By gluing together cohomology spaces of some fixed index of the fibers. Gluing, say, that's down here, so HI, there's something here, let's call this E pi x. We'll say with coefficients in C, and we get a finite dimensional local system of C vector spaces. And maybe as an arrow from there, we can get representations of, say, some connected, all that stuff. Here, representations of HI. So monodromy might appear in this way. Another way that I could mention is that, maybe more in the spirit of the conference, is perhaps starting in the analytic category, showing that associated to any connection, you have a differential equation, which is basically the one stemming from parallel transport via the connection, analytically continuing solutions or germs of solutions to that differential equation around loops, and obtaining monodromy in that way, and getting some algebraic notion of monodromy by considering the Zariski closure of representations of that in GLN C, since that's not an analog. And then you have a differential Galois group that you show that algebraic monodromy embeds in a la cats in this video. So monodromy appears here, not necessarily via this approach that I had geometrically. And one last thing I want to say before moving on to arithmetic is that, is that there is a correspondence that I'll state in maybe one or two ways that can be strengthened between monodromy and Galois representations. And one very simple, possibly natural way of seeing such an analogy is as so. So just analogy between for instance, you can take, stick with M, I suppose I used that earlier. You can consider pi1m, consider subgroups, and then we can consider the trivial subgroups, and show V an equivalence of categories we have between representations of pi1 and covering spaces of M, and connecting and such, that these correspond to covers, this corresponds to M. These are dominant covers, so the degrees are increasing. They contain those that are above them, and they terminate with the correspondence between the trivial group and the universal cover of M in such a way that the degrees of these covering spaces correspond to, what we say correspond to line, I suppose. They correspond to the index of the corresponding subgroup in pi1. Did I not flip those?
Inclusions, yeah.
Well, they're not.
Inclusions anymore, right? There's two guys.
Yeah.
There should be arrows. Right?
Yeah, sorry. Right. Okay, I see. Thank you. And over here, we might have, we say with a field of characteristic 0, or I could say perfect and talk about separable closures, but here we'll look at Gal bar K, and we can consider the trivial group in there. And then we have a correspondence here between these and the fixed fields. So here we get to K, and here we get to K bar. And likewise, the degrees of the extensions here correspond to the index of the subgroups here. So there's some kind of analogy between these two pictures, and it can be strengthened in various ways to show that in a setting where you don't necessarily have a monodromy in this sense, you deserve to consider the Galois representation in place of maybe something else I could say is that the absolute Galois group. So here we've got, via this correspondence, representations of pi1 of the monodromy controlling covers on M. And likewise, you could consider the absolute Galois group to control covers of open subsets of the places of Q. So maybe arithmetically you can see that these deserve to take the place of mono. Okay. So in our picture, we have sitting over take the z of 1 over m, so n. I could just say m is 2, but we'll say m even. So in this setup we put a connection, an Bell connection. And a connection G was just a family indexed by some odd primes. I'm just going to go right to the ellipse of Frobenius. So we'll say it's a family of these phi p's, which are ellipse of Frobenius, corresponding to some p-derivations. Each one maps to itself. And the p's are in some set of primes, some set of odd primes, possibly finite, possibly maybe. So the previous connection is global law 1, where this 1 is the identity matrix. So if we wanted to fix the ideal of 1, and so we get, by fixing the ideal of 1, we get induced phi p's on p-adic completion of A. Well, let's see what this. So we get induced phi p's T be the ideal corresponding to 1 of certain indeterminants, and of course this X here is a matrix of indeterminants. We get induced maps like this. These are actually those are just those. And in addition, we wanted to send, since in here we have A of t, we can require fix A of t, which just corresponds to that picture that was drawn. So here we get induced ellipse of Frobenius on the A of t's by these two conditions being present. So given these, we can define curvature. So we define the curvature of so this is the family. So, yeah, P prime, two different choices of primes in my set P, where prime is commutator of these two measures. So we've got a connection, we've got curvature. A natural question to ask is, what holonomy is associated with this thing? Now that would be a question maybe more akin to a question on affine connections. So I'm actually going to look at the canonical connection, the Chern connection. Chern connection, satisfying. So we put some, if we require that some properties be satisfied, some compatibility conditions, we get this unique Chern connection. And each of these Chern connections depends on some matrix little. I didn't use p primes. So it depends on some matrix little q with entries in roots of unity or 0. All right? So let me do this. So I define, I'll define here a Hall 0. And this is the z-span of commutators of these lifts and consider the z-span in z endomorphism space. So first thing to try is via this exact sequence that I'm erasing right now. I will continue to. Holonomy, let's maybe start by filling in the blanks. That thing involved groups. What I define here is essentially a Lie algebra. So we have a number of questions to start asking ourselves just from the get-go. Here, what should I put here? I need something that relates to the restricted holonomy. Well, over here I gave you a definition of what deserves to be called the Lie algebra of the restricted holonomy. So to get a group here, you might want to, say, integrate via Baker-Campbell-Hobson to get to some group. So here, I'm going to put 1 here. I'll just say maybe integrate all 0. Will it work? I don't know. If it does, then what goes here and here? This deserves to be some kind of group that relates the two things here, this being the restricted holonomy, and this being the monodromy. So here you want monodromy, so you probably want some kind of Galois group based on this relation that I mentioned earlier. Well, perhaps you want absolute Galois group. Perhaps you want this, but this extension is non-abelian. So we run into a problem. Because if we choose entries of Q that aren't 0 or roots of unity, which correspond to the maximum abelian extension of Q, then we don't get curvature. We don't have globality along 1, which we needed in order to have these lifts with a ring in common they could speak with each other on. So we run into a problem with defining curvature. So maybe you think perhaps we can just take the maximal abelian extension here. So perhaps we take gal of maybe Rn. Say over Q. And now you have some other issues. Well, you do have curvature here, based on how we define the Chern connection. But one, it's not clear what might go in the middle that relates these two things to one another. Secondly, if we started out with this Lie algebra here. So here you might want a relation between that and the Lie algebra of this in some way. Some kind of Lie algebra associated with this. You could look at a group ring and take the Lie ring of that thing and consider an exact sequence of Lie rings. But this is abelian. So if I look at a group ring associated with this abelian group, I get something abelian, which means that the bracket is 0. It's not interesting. So there's a problem there. So none of these are really nothing I said here really leads itself to a satisfying solution. And maybe something else that's not very satisfying is that if we do resort to filling in these blanks and getting some exact sequence like this, there's still some bit of orthogonality between holonomy and this monodromy here. Their interaction is only with respect to something in the middle. Now, something in the middle might not have these things interact in a very satisfactory way in arithmetic. So there are some other options to sidestep some of these issues. We could consider some kind of completion. some kind of completions of these things, and avoid, say, the issues here with these being abelian and grooving and curvature being uninteresting as some kind of leeway. We'll try some kinds of completions. So maybe I consider something up here. Then I'll take, I'll call these G. G might refer to either of those, I don't know. Oh, I can't use G.
Gamma.
Yes, the other G, that's fine. So let's say Q gamma hat. So, based on what I said before, maybe you want to look at some kind of sequence like this of Lie rings, and we'll consider some kind of completion of it. Where here, perhaps, we might try defining this completion in this way, where I define this in terms of completions of some Hall-ends. These are images Hall to see the morphisms of A to T modulo the nth power of my ideal that I completed along, this global along. So this gives me some kind of completion of the Holonomy Lie algebra, and then here perhaps I can try one of two things. Perhaps
I'll ask you to wrap up a little bit, and just some people may have to catch.
So here perhaps we try Malchev completion, where we complete with respect to the augmentation ideal of this group ring here, or maybe a pro-unipotent completion, and see if we get something interesting, see if there's an interesting relationship there, and whether or not we can find something to put in the middle. Some other alternatives would be, rather than considering our A as over there, we consider a ring of integers with M inverted of some non-abelian field extension, so some non-abelian number field in the Q, finite, and do away with being global along one and try and be global along something else, like a diagonal torus, where we allow the entries on the diagonal of our Q to be not restricted to roots of unity, but arbitrary integers. So for instance, we could try something like that and put a bunch of restrictions on Q and see what happens. I think Alex tried that, and the restrictions were very interesting, let's say. Very restrictive, curious, unexpected, perhaps. And there are some other options maybe involving rings of correspondences that can do away with that restriction of the entries of Q happen to be in roots of unity, but it's also very mysterious. So I'll stop here rather abruptly.
So the condition for the zeta ends be clear from this talk. Where does the converting M come into the?
So in particular with this Chern connection, I won't write it out, but it involves a square root there. And the way we expand that square root is as a power series. So we wind up picking up, we wind up having to invert powers of 2. So that's why I mentioned earlier that I can simply choose M to be 2, which allows us to get the periodic expansion of that square root.
But is that the only use?
It's the most immediate use. So yeah.
2 is the worst thing.
Yeah.
But there are other moments when one needs. Sometimes you
one should take n equals to n, actually. To invert n as well.
No other questions, or thank you again.
Guess I'll end by having us thank the organizers again for a great meeting this weekend.